Hello viewers, welcome to this lecture on the relation between continuous and discrete systems. So, in this lecture we will see some results on the controllability and observability of continuous and discrete system and their relations. So, let us consider the control system x dot equal to Ax plus Bu, where A and B are constant matrices. A is a n cross n matrix and B is n cross m matrix. So, let J denotes the Jordan canonical form of the matrix A. So, there exists a non-singular matrix P such that P inverse AP is the Jordan form J. So, let P inverse B is the matrix D. Then we can show that the system x dot equal to Ax plus Bu is controllable if and only if the canonical system z dot equal to Jz plus Du is controllable. So, that is where z, the variable z is P inverse x. So, it is a transformation which we are making on the state variable. So, we have already seen that the system, the controllability of both the systems are equivalent because of this rank condition. The rank of B, AB, A square B, A power n minus 1 B is n if and only if rank of D, JD, J power n minus 1 D is n. Now, we consider the corresponding discrete systems. So, first corresponding to the discrete corresponding to x dot equal to Ax plus Bu, the discrete system is given in the equation 3 as x of k plus 1 equal to E x of k plus f u of k, where the matrix E and f are given by this E equal to E power Ah, and which can be written as P e power jh into P inverse. Similarly, the matrix F is given by integral 0 to h e to the power A theta into d theta into B, and A, because A can be written as P inverse AP is J. So, we can write A as P J P inverse. So, we get this expression. So, e power Ah can be written as P e power JH P inverse. This, wherever A is there, it can be replaced with the Jordan canonical form by using the P matrix like this. So, now, so this we have seen already how to convert a continuous control system into the discrete control system, and this h value is the increment in the time, discrete time. So, if the initial time is 0, then we consider 0 h 2 h etc. into n h k. So, into k times h etc. These are the discrete time intervals. At this discrete points we get the value of x, the state variable, and the control variable u of k. They are related by this relation. So, this has been seen in a previous lecture. So, corresponding to the Jordan equation, this expression z dot equal to Jz plus Du, we get the corresponding the discrete form as z of k plus 1 is E bar zk plus f bar u of k, where E bar is given by this, f bar is given by this expression. So, now as we have seen that the given matrix and the corresponding Jordan canonical form will have the same behavior for the controllability. So, we can see that the result corresponding to the canonical system 2 and 4. If you prove controllability on the system 2, then the system 1 is also controllable. Similarly, if the system 4 is controllable, then the system 3 is also controllable. So, that relation we can see using this result, the rank condition. Now, we consider the observability of the system. x dot equal to Ax plus Bu and the observation y equal to Cu, and the matrix A and B sizes have been taken. Now let us say C is a P cross N matrix and Y is P cross 1 matrix, which is the observation of the system. The corresponding canonical form is given by Z dot equal to Jz plus B du and Y is equal to G times Z, where G is given by, because Z is nothing but P inverse X. So, we will get G equal to C into P, because Y is equal to Cx and X is equal to Pz. So, when we substitute we will get Y equal to Gz, where G is given by the matrix Cp. So, we can now show that the observability of the system 5 implies observability of the system 6 and vice versa. Observability of 6 implies observability of 5. So, that can be easily seen by the rank condition. Observability of 5 means it is the rank of the matrix C, Ca, Ca square, Ca power n minus 1. So, the rank should be equal to n, and we can obtain from this the matrix A. So, here C is Gp inverse and next is Gp inverse and A is given by Pjp inverse, etc. So, Gp inverse A power n is given by P j power A power n minus 1 is given by P j power n minus 1 P inverse. So, we can get the rank of this matrix is same as rank of Gp inverse and G j P inverse, etc., G j n minus 1. So, P inverse is common for all these entries here. So, the rank of this matrix, but P inverse is a non-singular matrix. So, we get rank of this matrix is same as rank of G j to the power n minus 1. That is same as the observability of the system 6 here. So, we have shown that the observability of 5 implies observability of 6, and if we go in the reverse order we get observability of 6 implies observability of the system 5. So, both are equivalent. So, if we prove controllability and observability for the canonical system, it is equivalent to proving the controllability and observability of the given system x dot equal to Ax plus Bu and y equal to Cx type of thing. Now, the discrete system corresponding to 5 and 6 are given by the equation 7 and 8 here, where E and F were already defined and y of k is C times x of k is the same C matrix there, and G is defined in the previous slide for the Jordan canonical system. So, now the controllability of the continuous system and controllability of the discrete system, how they are related, that we can see in the coming in this slide. So, we have shown that if Si minus j inverse B has linearly independent rows as a function of S here, okay, as functions of S, then the system is controllable. x dot equal to Bu is controllable. So, if Si minus J inverse B has linearly independent rows, then the system x dot equal to Jx plus Bu is controllable and vice versa. Similarly, if Si minus e to the power Jh inverse into F has linearly independent rows, then the discrete system is controllable. That is the discrete system given by this equation, z of k plus 1 e bar z of k plus f of uk is controllable. So, now we will show we are interested in having the continuous system and the discrete system together to be controllable, because in many practical problems when we have a continuous control system, if the model is a continuous control system and when we solve it using discretization, so we will get the corresponding discrete system, and if the original system is controllable and if the discrete system is not controllable, then the result may not be very useful. Similarly, if the original system is observable and the discrete system is not observable, also is not a very useful result. So, whenever we want to handle a continuous system as a discrete system for numerical purpose, then the controllability, observability, stability, all the properties should be preserved in the discrete system. So, we will see here under what condition the controllability, observability of the continuous system also implies the controllability, observability of the discrete system and vice versa. So, here we have already proved that if this resolvent Si minus e to the power Jh inverse into F, if it has linearly independent rows as the function of S, then the system is, the discrete system is controllable. And so, using this we will come to the following conclusion. So, in other words, if Si minus e power Jih inverse into F suffix I, okay, has linearly independent rows, then the discrete system is controllable. That is for each I, for I equal to 1, 2, 3 up to k. The number of eigenvalues are k, that is lambda 1, lambda 2, lambda k are the distinct eigenvalue. For each eigenvalue we have the Jordan block Ji, and correspondingly F has the blocks F1, F2, Fk, and the Fi block along with this. So, if Si minus e power Jih inverse Fi, so if this matrix has linearly independent rows, then the system is controllable. For each I it should be valid. So, that is what we have seen. So, we can easily see that this block Fi, the nature of the expression Fi is given by this So, f is given by integral 0 to h e power a theta into d theta multiplied by the B matrix, but we are using J matrix here. So, f is nothing but integral 0 to h e power j theta d theta into the B matrix. So, if you assume like that here, so here f is integral 0 to h e power j theta d theta into the matrix B, whatever matrix B we are considering. Similarly, Fi means we have to replace it with j suffix I because of the Jordan canonical form, and B at the same time can be replaced by B suffix I. So, it is integral 0 to h e power j I theta d theta into B I matrix. So, instead of showing S I minus e power j I h inverse F I, we can show that this thing. So, if S I minus e power j I h inverse into B I has linearly independent rows, then the system is controllable. That is because you can see that Fi is made up of the matrix of the form integral 0 to h e power j I theta. So, e power j I theta will be commuting with this matrix S I minus e power j I h inverse. If we expand it, it will be in terms of e power j I h terms as a series expansion. So, it will be always commuting with this integral e power j I theta. So, we can write F I in the other side also. So, instead of writing S I minus e power j h inverse F I, we can write the, so if you write F I as some matrix, say M matrix into B I, where M is given by integral 0 to h e power j I theta d theta, that matrix is M, and it is made up of all this e to the power j h type of thing after putting the limits. So, it will be commuting with this matrix S I minus e power j I h inverse. So, we can write this M in this side. So, and we can also see that this M matrix is non-singular because it is coming from a non-singular matrix e to the power j I theta, and we are integrating from 0 to h. So, the resulting matrix is non-singular. So, the row of this matrix, if the rows of this matrix are linearly independent, then the rows of without this M also will be linearly independent. So, it is enough if we check whether the rows of S I minus e power j I h inverse into B I are linearly independent for the controllability of the system. So, for the controllability of the continuous system, we have to verify this one S I minus j inverse B rows are linearly independent, and for each I again we have to do S I minus j suffix I inverse into B I should have linearly independent rows for the controllability for each I. Similarly, this matrix should have linearly independent rows for each I for the discrete system. Now, we will see that in some cases the continuous system will be controllable, whereas the discrete system will not be controllable, for the corresponding discrete system may not be controllable. because if you see that if lambda I and lambda j are, let us say, two distinct eigenvalues, they are such that the real part of lambda I equal to the real part of lambda j, but imaginary part of lambda I is imaginary part of lambda j plus some 2 pi by h into alpha, where alpha is an integer. One, two, three, etc. So, if we have this type of expression, then we can easily see that they will have terms like e to the power lambda I h. Similarly, e to the power j suffix small j h will have terms like e to the power lambda suffix j h, and we can easily see that e power lambda I into h will be equal to e to the power lambda j into h. So, we will see that similar expressions will come as a function of s here, si minus e power lambda I h e to the power j I h, as well as si minus e to the power j suffix j h, both will have similar s functions, and there, and if you have the linearly dependent rows of B I matrix, then the theorem will not be valid for the discrete system. In other words, this will not happen, this rows of Si minus e to the power lambda I h inverse into Fi, they will not have linearly independent rows for all the values of I, because for I and j, if the eigenvalues are behaving like this, then the corresponding rows will be linearly dependent because of the nature of this expression. So, in such cases we will not get the controllability of the discrete system, whereas because the eigenvalues are distinct here, the continuous system is controllable, but the discrete system will not be controllable for this case. So, for example, if we consider j to be like this 1 0 0 and 0, because it is a diagonal matrix, these 3 are the eigenvalues and the real parts are same, imaginary part are like this 2 pi I here, sorry, 2 pi I by h, and this is 1 minus 2 pi I by h, d is 1 1 1. Then the Kalman condition d j into d is the second column, j square into d is the third column. So, we get the Kalman condition like this. This has rank 3, so it is non-singular. So, this implies the system is controllable. The continuous system x dot equal to jx plus this du if you take. So, this system is controllable, but the corresponding discrete system, if we take, when we convert it into discrete system, we have to calculate e to the power ah, which is given by this. Here it is j, a is equal to j in this case. So, e power ah is given by these 3 eigenvalues, that is e power h and e to the power h into e to the power 2 pi I by h into h. So, that will be 1. Similarly, here. So, all the 3 will get only the terms like this. So, e power 2 pi I is 1. So, we get all of them are e power h only. Similarly, e to the power j theta into d theta multiplied by d for the control matrix, we get this expression. So, now you can easily see that this is our E matrix and this is the F matrix. So, if you calculate F and E times F and E square times F, and the rank of this will be equal to 1 only. So, this system is not controllable, but whereas the corresponding continuous system is controllable. So, it depends on the H value, or the eigenvalues should not behave in that particular manner. Here we can see that the eigenvalues are like this. The real parts of this and this are same, real part is equal and imaginary part is the imaginary part of the second eigenvalue is 2 pi I by h, and imaginary part of the third one is minus 2 pi I by h. So, their difference is, so if we take this one, their difference is this expression plus 4 pi I by h. So, this expression. So, according to the theorem, the imaginary part should not differ by this type of expression. So, in that case it will not be controllable, the discrete system is not controllable like this. Similarly, we can do the same theorem can be repeated for the observability. If the real parts of two eigenvalues are the same, but imaginary parts are differing by 2 pi by h into some integer, then this observability of the continuous system will not imply the observability of the discrete system. So, we have to choose carefully the h value, that is the conclusion that the incremental time increment h should be chosen carefully, so that this eigenvalues will not behave in this particular manner. So, in this lecture we have seen the relation between the continuous and the discrete system and their controllability, observability properties. Thank you.